Okay, so if you recall, last class we were doing analysis of a steel section. Okay, we have seen that the effective EI in that case comes out to be BD cube by 12 into E of steel. Okay, and we have also calculated the ductility. So we represented the moment versus curvature curve, which was, in case of the steel, it was linear, then it was curved, and we represented it by equivalent bilinear curve, something like this. Phi 2, we have calculated, how much was that? Ultimate curvature? 2 epsilon u by y, and we have calculated phi y. How much was that? 3 epsilon y d. Okay. Phi y dash was 2 epsilon y d, but that we increase to 5. Okay. Now same thing, let's do in the presence of axial force. So when an axial force here, the axial force was 0, then we have applied an axial force equal to 0.25 Fy into Bd. In presence of this axial force, what happens to the moment curvature curve? Have you tried? Do it here if you have not tried. We have started in the last class.
Yes.
So the only difference in case of axial force is that now C is not equal to T, other expression will remain same. C minus T will be equal to T. So let's do what happens to the value of m y dash. So m y dash is corresponding to the first T, where the extreme fiber is yielding. So how much is that moment? We have checked that also in that case, and we have seen that it is reduced. Okay, and we also discussed the PM interaction curve in case of steel section is different than that for reinforced concrete RCC section. Okay, in RCC section the capacity is increasing with axial force initially, and then it reduces. It achieves a maximum value of moment capacity corresponding to what we call balanced failure. Okay. But in case of steel, the moment capacity started decreasing as soon as some axial force is applied. So that is the difference between the interaction curve for steel and concrete. And why that difference? That also we discussed. Why there is a difference? We discussed it. That difference is because in steel the stress strain behavior in compression and tension is identical, whereas in case of concrete, in tension the capacity is much lower. So when we are providing any axial force, it is putting more section in compression. Okay, so there it helps. But in case of steel section, it is not helping. So this value we obtain BD square over 6 Fy in case of P equal to 0, and in case of P equal to 0.25 Fy BD, how much was that? BD square by 8. So it has reduced. What happened to the stiffness? We have calculated phi y dash also. So is the stiffness same or stiffness has changed? Calculate phi y dash. for the same section which you have already analyzed. So the moment capacity has reduced, what happened to the curvature? You have calculated neutral axis depth. How much was neutral axis depth?
2D by
In presence of axial force.
2D by
2D by 3. Okay. So if Fy or stress in compression extreme fiber is Fy, how much will be the stress on the tension side? From linear distribution of strain, so how much strain you are going to get on compression side? It will be less than Fy.
Yes.
How much?
.2 d minus epsilon minus Fy by 2.
Fy by 2. So how much will be the curvature? Phi by dash.
Yes, 3 by 2 epsilon y by d.
So phi by dash in this case you are getting as
3 by 2.
epsilon y plus epsilon y by 2, okay, divided by d. So that will be so how much will be the stiffness? M by dash divided by phi by dash. How much you get? It's a very simple deal. VDQ by 12 Fy. Okay, sorry, Fy will cancel. So E you will get. So E into VDQ by 12, which is same as in the previous case. So there is no change on the stiffness. Okay, stiffness remains same. Only thing is that the moment capacity has reduced. Then from here it will follow. We can use a bilinear curve. Can you calculate phi u in this case? Whether it is increasing or decreasing. Calculate mu and phi u in this case. So I have obtained only m by dash. So it will not be flat from here. Okay. So can you calculate mu and phi u? We discussed that in case of mu, you can assume that the whole section has developed Fy. And the total depth is d. So can you calculate Xc? So that C minus T is equal to D.
It's equal to 5 by 8 d.
Huh?
It's equal to 5 by 8 d.
X equal to 5 by 8 D.
Yes. And
How much is mu?
mu equal to 11 by 64.
Mu is equal to
11 by 64.
11 by 64.
Fy by d square.
Fy
d square.
d square. Okay, so is it more than the previous case or less than the previous case? 11 by 64. The mu which you have obtained without axial force, how much was that? BD square by 4. At least that we can do. That was BD square by 4. It is 11 by 64. BD square by 4 is nothing but 16 by 64. BD square. Okay. So that was 16 by 64. It is 11 by 64. So it is less than the previous case. Okay. Is it greater than m by dash or less than m by dash which we have obtained? Okay. BD square by 8. It's more than that. So that means that it will increase further like this, but it will be less than the previous case. So moment capacity has reduced. Okay. Initial stiffness is same. Can you calculate the phi u in this case? In presence of axial force, you already know neutral axis depth. You know the strain, ultimate strain. So can you calculate the strain diagram? Here it is epsilon u. This is 5 by 8 d. This is 3 by 8 d. So how much will be the epsilon here? It won't be epsilon u. It will be less than that. How much? Sorry? 8 by 5. 3 by 5. So this will be 3 by 5 epsilon u. So how much will be the curvature? 5. So by u in presence of axial force, that is equal to 3 by 8 epsilon u plus 5 by 8. No, sorry. Epsilon u plus 3 by 5 epsilon u divided by d. Okay. So that is 8 by 5 epsilon u by d. It is more than the previous one or less than the previous one? 5 by 8. And here it is 2 epsilon by 2. Sorry, 8 by 5, no? 8 by 5. And this is 10 by 5. So it is less than that. So this is 8 by 5 epsilon by d. Can you calculate ductility ratio in the two cases? With p equal to 0, our curvature ductility is how much? Two epsilon u over d divided by 3 epsilon y by d. So that will be equal to 2 by 3 epsilon u over epsilon y, 2 by 3 of mu epsilon. Agreed? And when I have applied axial force equal to 0.25 SYBE, 25%. of its capacity, then how much is mu phi now? Eight by 5 epsilon u by d divided by divided by, in this case, how much was 5y? Will it be 3 epsilon y by d or it will change? You will convert this also into an equivalent bilinear curve and you will calculate 5y here. So how much will be 5y here? You will increase 5y dash in proportion of mu by m by dash. Please do that. It is linear. You have calculated 5y dash. So 5y will be increased in the same proportion. So 5y is 5y dash into mu divided by m by dash, because my is equal to m. Yes? 11 by 8. Epsilon y by d. Okay? That's what we have got. Cross check. What you are looking for? Is anything missing? How much? 33 by 16.
Yes.
Not 11 by 8. So is it more than the previous one or less than the previous one? Earlier it was 5y dash. Earlier, sorry, 5y.
B is equal to 0.
At p equal to 0. That was 3 epsilon y. So is it more than that or less than that? It is slightly more than 2. 2 point something. So this is also less than that. Okay. So can you calculate now the ratio? Mu phi as, okay, we have already written here. So divided by 33 by 16 You can calculate in decimal.
Excuse me.
Huh?
Excuse me. How does that become empty? Should not it be only one instead of two?
Yeah, because you were not present in the last class, and there we have seen that in case of steel, this curve is more or less flat. So mu and my are equal. So in equivalent bilinear curve, my is close to mu. So how much is mu 5? 0.77. So let me say 0.78. So what has happened to the ductility in presence of axial force? It has increased or decreased? Increased. Look at this curve. So what do you think? Which one is going to dissipate more energy? Which will have larger hysteretic curve? And you have discussed in the last semester, we discussed that the energy dissipated will depend on the area of the hysteretic curve. So which is going to have larger hysteretic curve? With P equal to 0 or with P equal to 0.25 FYVD?
P equal to
0.25? This will have larger hysteretic curve? Or this one will have larger hysteretic curve? Which one will have larger hysteretic curve? You can draw the hysteretic curve and see. How the hysteretic curve? You will take this line parallel to it. So one curve is this, the other curve so which one is larger?
P equal to 0.
But that one is having more ductility. Okay, so this is the limitation of ductility ratio, because ductility ratio depends on the ratio of epsilon y. Okay, phi u divided by phi y. So if there is a change in phi y, okay, this ratio is misleading. So ductility ratio in some cases can mislead, like in this case. Actually, the ductility capacity has reduced. The energy dissipation capacity has reduced. Okay. So, can you think of a better representation of ductility other than ductility ratio? That is the plastic curvature, phi p, which is phi u minus phi y. That is a better representation. Ductility ratio in some cases can lead to wrong conclusions. Like in this case, the conclusion is wrong, that in presence of axial force, the energy dissipation capacity is increasing. Okay, that's not correct. Actually, it is reducing. So, any doubt up to this point regarding the behavior of steel structures, steel sections rather, subjected to moment with or without axial force. Okay. So, important thing you notice here is that the stiffness in all the cases, whether axial load is applied or not applied, the stiffness remains same, EI BD cube by 40. Okay. Now let us see, let us extend this to RCC. Suppose
Sir,
this, yes,
what is the 5T portion?
5P. Okay. So 5P is the difference of phi u and phi y. So in the first case, when axial force is 0, this is 5P, and when the axial force is 0.25 FYVD, then this is 5P. So this is the plastic curvature. What is plastic curvature? The difference of ultimate to elastic curvature. So difference of these two curvatures. In the same manner, we will see later, we will calculate displacement ductility and plastic displacement. So plastic displacement will be delta U minus delta P. We will do it later. Okay, and that will depend on this phi P. So this phi P is a good indicator. Okay, so on the same lines, we can define theta U and theta Y. You can guess what is theta U? Ultimate rotation divided by yield rotation, and we can have delta U divided by delta Y, or delta U and delta Y, ultimate displacement and yield displacement. You will slowly go in that direction. Okay.
So
Any other question? Yes.
This 5P is similar to the lack of impact, like in steel stress data.
Yeah, it is something similar to, there we can define epsilon P, the plastic strain. What is plastic strain? Ultimate strain minus yield strain, which is defined in our code as 14.5% minus epsilon U. So total elongation is 14.5%. So that is epsilon U minus epsilon Y, which is small. Okay. How much is epsilon Y? Of what order? Let us say in mild steel. How much is epsilon Y? These parameters should always remain in your mind. 0.125%. So out of 25% or 14%, 0.125. Okay, that is very small. You can even ignore. Okay. So that 14.5% you can treat as plastic strain. So the steel should have minimum plastic strain equal to 14.5%. And similarly, you can, based on that, you can calculate the plastic curvature. Okay. Any other question? So the same column, let's continue. Only thing is that this time, let us say it is a steel cell, sorry, RCC cell. Previously it was steel, now let us take RCC. In case of steel, we have done assuming B, E, etc. Here it will be easier, it will be difficult to continue the calculation in terms of general dimensions. So let's take some numerical dimensions. So let us say this is 400, this is 300 millimeter, and I have 3 steel bars, let us say, and these steel bars of 25 diameter. And grade is I think 500, and here we have and 30 length.
column section.
W reinforced.
No, I want to still give like this. Why you want to make your life more difficult? If I will give reinforcement on the four sides, the calculation will be more complex. But the procedure will remain same. So don't worry. In the exam, I will give that one. But let's do it here.
Practically, it's not possible the column for multiple spaces.
Yes. Practically, there will not be any such columns. Just a column standing in the middle of nothing. Okay. So we will move to practical cases slowly. First we will do simple cases. Then slowly we will move to the practical cases. Practically it is going to be a frame, a building. Okay. So we will move to that. We will come to that. But let us start from understanding what is happening at a section. So if you have a section of a beam or column, what is happening there? Let's try to understand that first. Then we will move to more realistic cases. From section, we will go to cantilever beam. From cantilever beam, we will go to frame, single story frame. From single story frame, we can go to multi-story, multi-way frame. Okay, so slowly we will move in that direction. Let's first do this. So I have taken this section. On the tension side, you have reinforcement. On compression side, there is no reinforcement. Just to simplify for that. The procedure will remain same. You will assume neutral axis depth from the compression phase, let us say axis. You will assume a strain profile. So you can, let us say, assume strain in steel as epsilon y. Okay. You can calculate strain in concrete. Then you can calculate C and T. Equate C equal to T. Calculate axis. Let us do that. So let us assume that the steel has just yielded. So at that point where the steel has yielded, let us calculate M y dash and phi y dash. We are assuming that epsilon C is less than epsilon Cy, the yield stress, yield strain in concrete. How much is the yield strain in concrete? 0.002. No, that is not yield. That is the strain corresponding to the peak stress. So peak stress cannot be yield point. Okay, yielding occurs before that. So you recall the stress strain curve of concrete which we discussed. The stress strain curve of concrete, the realistic curve is like this. We replace it by this curve. This is 0.002 and this is 0.0035. For actually this curve is also not plotted correctly, it is parabolic. These are the curves. Okay, so you have to represent it by equivalent bilinear. So you have to draw a line from here, you have to draw a line from here, and wherever these are meeting, that is the yield strain. So can you guess how much is the yield strain? It is going to be less than 0.2. So there is no clear yield point which you can define like we have in the mild steel. So in case of all such materials, what we do? We represent these by equivalent bilinear curve. And where the two lines in the equivalent bilinear curve are meeting, that we define as the yield strain. The yield strain here we take as 0.00. So let us first assume that steel has yielded in our section, concrete has not yielded. So how the stress diagram will look like? And in steel, we have diaphragm. Can you tell me how much will be this stress? First, calculate epsilon y. And actually, it will not be Fy, it will be Fye, the expected stress. So in concrete, how much will be the maximum stress? First calculate how much will be the maximum strain, and then you can calculate the corresponding stress from the stress strain curve. So first tell me epsilon c. How much will be epsilon c? Let us assume the depth of the neutral axis also. Let us say for simplicity it is 100 millimeters in the first case. Let's say I have assumed the depth of the neutral axis as 100 millimeters. Cover in case of beam you can take 25 mm. Okay, 25 mm is the clear cover. So you can take up to the center, the effective cover. 25 plus 25 by 2. So 37.5 will be the effective cover. So for this depth of neutral axis, calculate epsilon c and check whether our assumption of assuming epsilon c less than epsilon cy, is that okay? How much will be the yield strain in steel? For Fe 500? Yes. Why we are? Okay, because we are calculating the stress, strain, moment capacity of the section. Suppose this section you have to test. When you are testing, what you are expecting? That we are trying. Not what you are designing. The expected stress. I also told you in the beginning of this course that in performance-based design, we are checking displacement, not the force. So when we are checking the displacement, the calculation of strength capacity will be expected. So we will be calculating expected strength. Always we will be using expected strength. So please use expected strength for calculation of epsilon sy. Either you can take 500 plus 1.64 sigma, or you can take it 1.25 F. No, Fe 500. Fe 500.
8 by 21 times of x1 is
Sorry?
8 by 21 times of x1 is
So you calculate that. You put epsilon y also. Let's see.
now 2.38 into 10 raised to minus 6.
Is it?
Into Fy.
F1. In epsilon y, there should be F1. You put value of Fy. Strain will be just a fraction. It can't be Fy. Put the value of Fy. I have put the value of E here. 1.25 to convert Fy into Fye. I have taken Fye here 1.25.
Sir, we can do that by adding
Huh?
1.65
Sorry?
We can do that by adding 1.65 sigma also.
1.65. Yes, you can do that as well. If you know the value of sigma, you can do Fy plus 1.4 sigma or 1.25. This 1.25 Fy I have taken from ASC 41. Okay, and ASC 41 is for American steel. So there they have specified 1.25 Fy as the X factor. So it will depend on the manufacturing process, how good quality control is. So this factor will depend on the quality control. If the quality control is very good, this factor will be small. If the quality control is poor, the factor will be large. So 1.25 into 500 divided by 2 into the power 5. Why it is taking so long to calculate? 0.0031. I will say 0.31. Okay. Then you can give me epsilon c. 0.00112. Okay. So you can see that epsilon c is less than epsilon cy. So our assumption is okay. What we assume that the steel is yielding fast, not concrete. Suppose this was greater than 0.0015. What does that mean? Suppose this came out to be 0.0017. What does that mean? It means that the concrete has yielded fast. Okay. So in that, concrete will control the yielding, my dash and phi by dash. Okay. Usually steel will yield. So with this, now can you calculate C? Okay. Before that, you were supposed to tell me the value of FC here. How much is that at this strain?
Sir,
Yes.
with epsilon S going what you said, plus we have said 0.002 also for every 5.
0.00?
0.002.
What is 0.00?
Because
But proof strain is not yield strain.
when you calculate yield strain, that should be added.
No. Okay, let's go back to the previous semester where we discussed the stress strain curve of steel, Fe 500. So it was like this. And when you were drawing parallel to this, why we were drawing parallel to this? Because some plasticity has occurred, and if we do unloading from here, then the loading and unloading curves will be parallel. Okay, we discussed that. So this was 0.002. Okay, that's why we call it 0.2% proof strain. But how we will obtain the yield strain? In case of mild steel, obtaining yield strain was very easy because we got yield plateau from where the yield plateau was starting. We were able to get how to get here. Is this strain yield strain? how much is the yield strain or the permanent strain in yield at yield point? It should have been 0 theoretically. Okay, so this is not yield point. This is the point where the stress reaches Fy. Beyond that it is flat. Okay, from here the yielding is starting. So what is the method in such case where yield point is not specifically defined? Equivalent bilinear. And what we will do for equivalent bilinear? We will draw a line from here which should pass through this first yield point, and then we will draw a line from the ultimate point. Okay, area under the two curves should be same. So actually this curve should have been slightly lower. Okay, so that this additional area which we have got from here should be equal to this area which I have left. Okay, but we can see that this area is very small. Okay, so we can treat that the second line in our bilinear curve is horizontal only. Okay, so we take it corresponding to this one. So where these are meeting, that point will give us epsilon 1. And how much will be that? This Fy, we are using expected strength. We remember that E in case of steel does not depend on the grade. So if we are converting from characteristic strength to expected strength, the modulus of elasticity E will remain same. That is not going to change. But same is not true in case of concrete. In case of concrete, with grade, the modulus of elasticity also changes. Okay, so we can calculate this epsilon y as Fye divided by EC, not EC, ES. Okay, so that will be 1.25 Fy over 2 into 10 to the power 5. That's what we have taken. So with this, can you tell me how much is the stress here? In the extreme concrete fiber, when the steel is used, how much is the stress in extreme concrete fiber? Will this be in the flat portion of the stress strain curve of concrete or in the parabolic portion? Parabolic. So you have to use the parabolic equation to get this stress. IS. Sorry?
25.
How you have calculated? Fy dash and Fy. FC you can say. Not Fy. Fy we write for. How much is the value of FC which you have used? 30. Great. Can you use same? Is the strength of concrete in beam or column is same as the fuel strength? So it can't be 30. So first of all, for calculating FC at any point, okay, or let me call it not FC, okay, we can keep FC 2 epsilon over 0.002 minus And how much is here? Here it is the strength of concrete in structure. So how much is that? This FC. Yeah, it has to be expected strength. So expected strength there for M30 grade concrete will be how much? Okay, and the strength in cube and number is same. So why not you are saying that? So it will be 0.67. Okay, 30 plus 1.64. Let us say sigma is 5. Okay, into 2 epsilon in our case was 0.0012 divided by 0.002 minus yes. We are using no. What is M30? 30 in M30, what is that? Characteristic strength of what? Cylinder or tube or what? Tube. Okay. Our grade in India, when we say grade M30, what is that? That the characteristic cube strength. So cube strength you have to convert into structural strength. What is the correction factor for cube strength to convert into structural strength? Point. That is not to structural strength. That is to convert cube strength to cylinder strength. 0.8 and then from cylinder to structure 0.85. So to convert cube to structure 0.85. Sorry, 0.8 into 0.85. So that comes out to be 0.67. Because we do not know the factor converting directly from cube to structure. Whatever value we get, not of cylinder, that will be in structure. Cylinder correction we have already done. If you have not applied 0.85, then you will get cylinder strength. You have also multiplied by 0.85, so you have converted first, or you can take it like this, that the factor to convert cube to structure is 0.67. Naturally, it is going to be lower than what is cylinder to structure, because cylinder and friction factor is not there. So, how much is this sir? Yes.
Why are we not apply 1.5 factor?
Because we are not calculating the limit state strength. We are calculating the expected strength. So we need not to apply any factor of safety. Okay. So in limit or what we call LFRD design. Okay. LFRD means load and resistance, LRFD, sorry. Load resistance factor design. So we apply a factor on load, we apply a factor on resistance, capacity, and then equate them. Why we apply these factors on load and resistance in limit state method? This is limit state. LRFD is limit state method. Why we do that?
We are understanding the material properties.
Why? We want to understand that. Because there is variability. Okay. And what we are considering is 95% confidence. 5% structures will still collapse, which we don't want. We want the collapse probability to be very, very low. So to cover that, we are using factor of safety. Okay. In case of performance-based design, we are not applying any factor of safety on capacity or force. We will apply the factor of safety on displacement later. You will see where we are going to apply the factor of safety. So here also there will be margin. there will be a factor of safety. But that factor of safety will not be calculated on strength. The factor of safety will be applied on displacement capacity. So we will calculate how much displacement capacity is in my structure, how much displacement will be occurring during earthquake, is there any margin there? That will be our factor of safety. Okay. So the strength capacity, we will not apply any factor of safety. Okay. We will consider expected strength. Okay. That means the most probable value. That means mean value. So we are calculating mean strength without any factor of safety. Yes.
Please repeat that factor of safety for structure and
That's not factor of safety.
No.
That is correction factor. So correction factor, you have seen here. So we have FC dash, that is a cylinder strength, that is 0.8
times of FCK.
FCK. Okay. And then the structural strength F, that is 0.85 times FC dash. So F is 0.67 times.
At first FC dash is from a cube to cylinder.
Right. So this is cube, this is cylinder.
Then second is from
Cylinder to structure.
cylinder to structure.
This is structure and this is cylinder.
And third one is
This is structure and this is cube. As written down. Okay, and all these values are 95% confidence. We want expected value. What is expected value? 50% confidence. Okay, or average value. Most probable value of any quantity. You have done in survey. Most probable value of any quantity is what? Mean value. So we are calculating, suppose in my building, I have hundreds of beams. Okay. So these beams are going to have different concrete strength. Which one I should take? If I am designing using force-based method, like what you have learned in your first semester, then I should use a factor of safety on the strength. We are doing displacement-based method. There we don't want to apply any factor of safety at or on this strength. So we will take the most probable value of strength, and most probable value of strength is given like this. So yes, how much is that from this equation? 21.5. Let me say 22 for simplicity. So this is 22 MPa. So now can you calculate C? You have done this in first semester also. And where is the catch? What is the catch in this? What caution you have to take? You will be integrating. So in integrating, what should be the limits? Limit should not be strain. Then you will get wrong answer. So the limit has to be in terms of distance. So convert strain in terms of distance, and then stress in terms of strain, and then you can integrate. Most of the times people substitute stress in terms of strain and integrate it with respect to strain. Okay, suppose you integrate stress with respect to strain, what you are getting? Which quantity you are going to get? Energy per unit volume. So we are not interested in energy per unit volume, we are interested in force. So the stress should be integrated per unit area. So to convert this into area, the width is constant, so B you can take out, and then you have to integrate stress with respect to XU. Over the whole XU, you have to integrate it. So C will be equal to D, that is 300. Okay. Integral from 0 to 100. Okay. And then stress we have already calculated. 0.67. Okay, so 0.67, 30 into 1.645, how much was that? 25.5. So and strain I have to convert into distance. So 2 times x, let us say, okay, into the peak strain, that was 0.0012, okay, divided by XU, that is 100. That is the strain divided by minus x into 0.0012 divided by 100 into Is it okay to put x in millimeter? I have put x here in millimeter. Is it okay? What should be the units? Units should be consistent, otherwise there will be problem. So do you think units are consistent if I put x in millimeter? How do you say that? Because F I have taken in Newton per millimeter square. So units have to be consistent and the result I will get in Newton. So B also I have to put in millimeter, X also I have to put in millimeter. So when I integrate it with respect to X, the limit should be in millimeter. So can you please simplify that and calculate C? Yes. Yes, you are right. Square. So other than X, everything is constant. So Tajal, when you are doing this hands-on class tomorrow, perhaps you can tell them in section designer to make the same section in steel and concrete, okay, and get the moment level check on section designer.
We'll do that.
You can. it will be good if you can derive the expression of C in terms of X. No, X you know, you want that. Okay, so go ahead. You can get only the numerical. You can't derive the expression. In that case, 100 has to be kept as XC. Yes. See, whatever is this, same will be, no, this is what, you are calculating C, D. So this FC is actually F. It is not FC, it is F, which is here inside the structure. So how much will be that? 0.67 into FCK plus 1.4 sigma. So it is not FC, it is F. Not 0.85, 0.67 bracket 30 plus 1.64 into 5. What we have obtained there by doing this. How much? C and D. 317 is C and D.
920.5.
And T? How much was T? 920.
Kilometer.
Kilometer. Okay, so you can see that T is much larger than C. So, what should we do? We have to take another depth of neutral axis, and the depth of the neutral axis should be increased or decreased? Increase. So, let us say XU and calculate C and T again. So repeat everything. Strain diagram will change, then stress diagram will change accordingly, and then you can calculate. T will remain same, but it is possible that with this XU, the strain in concrete may exceed 0.0015. That you should check. If it is exceeding, then our calculation will reverse. We will assume the strain in concrete as 0.0015, and then we will calculate the strain in steel. First calculate epsilon C. Epsilon YE was how much? Can you recall? Epsilon YE, the expected yield strain. 0.0031. So can you calculate epsilon C with x is equal to 150 mm? 0.002. That means it is greater than epsilon Cy. Okay. So for this depth of neutral axis, we have to assume epsilon Cy as 0.0015, and then we have to calculate epsilon St, steel intention, for this depth of neutral axis. That means concrete is yielding first. If this neutral axis depth, which we have assumed is correct, then concrete is going to yield first. So in that case, we have to consider yielding based on concrete. So My dash, which we call the moment capacity at first yield, it is corresponding to yielding of first fiber, which may be steel, which may be concrete. Okay. So which is going to yield first, that will depend upon the depth of the neutral axis, which is unknown. We are obtaining that IT2. Yes. How much is your epsilon Cy? 0.002, so that is greater than 0.0015. Yes, so that means the extreme fiber of the concrete has yielded, has strained more than the yielding strain. So the concrete has yielded. Concrete has yielded before yielding of the steel.
Correspondingly, that strain, we have to what is the value of strain in steel. We have to find.
Yes, now we have to find out that when concrete was yielding, at that time, what was the strain in steel, which will be lower than Fye. So the process is very simple. Same what you have done in your graduation. Only thing is that you should have good understanding of the stress strain curve of steel and concrete. That's it. Yes. Yes, we have obtained from equivalent bifurcation of the stress strain curve of concrete. So if I have to say when my concrete fiber has yielded, then I can say that at a strain of 0.001. So in this case, our process will reverse. How much is epsilon T? If epsilon Cy is 0.0015, point
0021
21
25.
25. So let us say 0.0021. So corresponding to that, can you tell me FST? $339.2. How you will obtain this? Okay, that will depend where you are in this curve. In this curve, where you are. If you are below this, then what you are saying is correct. But if you are here,
here we have seen that if we are taking EY there, then this concrete is getting more. So we are keeping it less.
when we were taking here, then it is more. But that doesn't mean that when we are taking here, then also it is more. So you have to check that this point is below this or above this. check whether this point is below. How much is this value of stress at this point? 0.8 FYE. And what will be the corresponding strain? So check whether the strain you have got is less than this or more than this. Less than this. How much is 0.8 epsilon by E?
0.0025.
Okay, so then only you can get the stress here at any strain as E times epsilon. So at every step you have to be clear, you should not make any error. So now calculation of C is very easy, you must be happy. In this case, how much is C? 2/3 of the corresponding rectangle. It is not complete parabola. No, I'm sorry. It will be complete parabola only when it is up to 0.002. So yes, now also we can't do it to 2/3. So we have to use integration in this case also. Yes.
So, we are managing FST. This will all FST
So strength is expected. Stress is not expected or characteristic or anything. Stress is the value. Strength may be expected or characteristic. Stress is the stress. So if you have to calculate force, it is stress and area. There is no issue of characteristic or because stress is what is occurring. It is not based on the test. Expected comes when we talk about strength. So what will be the change in the previous formula? In place of 100 it will be 150. Okay. In place of 0.0012 it will be 0.0015. Rest will remain same. See, this is the curve, let us say, of or the characteristic curve. Okay, what will happen in case of expected? Or let's first go. When you have applied a factor of safety, how was the curve looking like? When you applied a factor of safety of 1.15, so was the whole curve going down? It was going like this. So below this point, it is only E into epsilon. No 1.25 or anything. So it will be simply E into epsilon. If it is less than 0.8. But if it is beyond that, then of course you have to take that into account. Okay. First, see, forget about it. First you plot the curve of the steel which you are expecting. So curve of the steel which you are expecting, let us say this is for Fe5. I have already written FIE, I will delete that. So, let us say this is white curve. And this blue curve below, this is for Fe 500 divided by gamma. Okay. For expected strain, what will be the curve? The expected stress strain curve will be, how that will be looking like. It will be, let me use another color, I will use yellow. So it will be following the same curve, okay, and then it will go like. And how much will be this value? This value will be Fy. If you have to calculate stress corresponding to any strain on this curve, what will you do? You will calculate 0.8 of this from here, and if your strain is lying below this, then it will be simply E times that strain. Okay, 1.25 is not coming. But if it is here, let us say strain, then 1.25 will come. So plot the expected stress strain curve and read the value of stress corresponding to the given strain from that curve. Now let's extend this to concrete also.
Sir,
Yes.
when we calculate the epsilon y, we have considered the 1.25, and with the help of this we can calculate the epsilon c, means 1.25 considered strain in strain versus factor. So it is automatically considered 1.25 if we have multiplied epsilon into.
But we have not considered epsilon y, we have considered epsilon cy, that is 0.0015 in this case. So here we are not considering strain in steel, we are considering strain in concrete, 0.0015, that is constant.
Yes, sir.
So there is no factor of 1.25 coming here in this case. Okay, so don't think this way and that way. Be clear, straightforward. First plot the expected stress strain curve. What is the expected stress strain curve? You plot that and read from there. Simple. Why you are thinking that 1.25 or multiplied here and there? What is the expected stress strain curve? This yellow color. This is what is given in the code, and this is when we apply a factor of safety. Okay, so I have to read the corresponding curve. When I was doing limit state design, I have to read this curve,
Yes, sir.
not this one. We have read this curve. Actually, this curve is not used anywhere. This curve is used only to obtain this curve and this curve. But actually, in limit state design, we were reading this curve. Now here, performance based design, we are reading this curve. So first plot the curve which you are expecting, and then just read that curve. Now what will happen in case of concrete? There is issue. What is the expected stress strain curve? Got it? Like we have done in steel, what is the expected stress strain curve in structure of code? So how that will look like? So is it more than FCK or less than FCK?
More than MC.
But I am asking you the expected stress strain curve in structure, not in cube. or cylinder?
Less
More than or less than? At least you can calculate for M30. Okay, so in this case, this strain, there you have seen that the yield strain was changing. In case of concrete, the strain remains constant, and then the modulus of elasticity has to change to keep the strain, yield strain same. Okay, so here the curve will look like you have to read this or you have to calculate C and D, sorry not T, C based on this curve. So we will obtain, first we will estimate the expected strain, okay, based on the depth of the neutral axis. I will calculate the strain. Then using that strain, I will read the stress in steel and concrete based on the expected stress strain curve. And then I can calculate C and D.
So that curve will be FCK plus 1.64 sigma, that value will go up.
Because it is in structure. FCK when I have written, this is in cube. So I have to convert cube to structure, and I have convert 95% confidence to most probable value. So let's go back. Yes. Sorry? Huh? Previous. This one?
FST 424.
FE?
FST 424.
424, not 339. So can you calculate CMT now? So you can see that it is a cumbersome process, isn't it? Every time you have to, should we study that? There is software, we will teach you tomorrow, which will give you a moment curvature curve directly. Is there any point in studying this? Should I have taught, or I should remove it from the syllabus? We go directly to the moment curvature curve value we will get from software. Software tool is already.
You don't get the one of the software is doing.
And still now there are bugs in the software, and you will find most probably your value which you have calculated will not match. Okay, because the values or the stress strain curve which software will be taking and which you are taking may be different, and what software is giving may not be correct. So for that it is important that you understand the whole process. That's why we are doing it. And In the exam also I will ask it. So do practice. If you are not practicing it, you know from your experience from the first semester that these sections, these are very simple, but even in the final exam, you were not able to do it. The simplest question you were not able to do, just because you are not practicing. And I can also tell you in the exam, it will not be just simple rectangular beam and you will go by his advice. He has already suggested that you should provide reinforcement on all the four sides. And then there is going to be confinement also. So you have to use Mender's model to get the stress strain curve. Here I have taken a simple unconfined section. There is no confinement. If I then this stress strain curve which I have plotted here, this is valid. If it is confined, then the stress strain curve is going to be changed. And for that you have to use Mender's model or any other model. There are other models also for confined concrete. If you are not happy with Mender, you can use any other model, and I will be very happy if you use any other model. No, bilinear curve we are doing only to obtain yield straight. Sorry, C is how much? 607 kilonewton and T 625. Not exactly equal, but let us assume we are happy with it. C is equal to T. So can you calculate then M y dash and phi y dash? For calculating my dash, the most difficult part is calculating the point of application of C. So if you have to obtain it, how you are going to obtain? Point of application of C. Let me call it x bar. So how to calculate x bar?
Two times integration of this.
Sorry?
2 times integration of this.
2 times integration means double integration. Why? Why you want to do double integration? Double integration, I mean, when you integrate it once, you will get force. When you integrate force, what you will get? If you integrate force with distance, what do you get? Work done? But we are not interested in work done. Sorry? Integral? Right. Okay. x bar will be 0.67, okay, FCK plus 1.64 sigma, which we have obtained, okay, and actually that will cancel out, we will see later. So integral 0 to 150 in this case, and 2 times strain. Strain is how much? Yes, in our case strain is how much? 0.0015 divided by 150 into fine into x okay, divided by 0.002. So that I can write here. Okay, into x, that is the lever, okay, of this small force, okay, and b I will take outside minus this whole thing square divided by 0.67 FCK plus 1.4 sigma b 0 to 150 2 times 0.015 x divided by 150 into 0.002 minus, so this will cancel. Integrate this. So it will be x square in place of x in the means. That's it. You agree what I have done? Dx I forgot to write. Yes. You don't get it? Okay. So our stress diagram is something like that. If I take at any distance x from here, this is x.
Corresponding to that.
Right. And let us say this is dx. So if I integrate f into x into dx, what I will get? The moment about this. Okay. So moment divided by the force. What is force? F dx. So this is giving us the force, this is giving us the moment. So moment divided by force is the distance of the force application or point of application of the force x bar from neutral axis. So keep in mind that this x bar is from neutral axis. Yes. You have to multiply by I have not written the second, so second will be this. Same thing is square.
Q. Sir, x will become Q.
Okay, hold on. X I have to keep outside, not inside. So this is stress. Stress I have to multiply by x. X will be outside. I would have moved it. Here, you are right. I can move it here and write it properly rather than doing it. So this is f. I have written f x dx divided by f dx. Tired? हाँ कवन हाँ yes you are right you are right. क्या हुआ? Okay. चाय चाहिए? 4 to 6 की क्लास में चाय होना चाहिए। समोसा भी? बिस्किट से चल जाएगा? हाँ? 95.83. What is that? X bar. Huh? Oh. So can you calculate m y dash and phi y dash? And then EI. M by dash is how much? 192.9. 192 units per meter. So millimeter you have already converted into meter. And then phi y dash. Yes. COT कैलकुलेट करने के लिए, ओके। C कैलकुलेट करने के लिए COT कैलकुलेट करने के बाद क्या किया? We are calculating M and it is beam, so we can calculate M about any axis. So let us calculate about neutral axis. So C I already know, C into x bar plus T into D minus XE. Let's take moment of both the forces about any axis, neutral axis in this case. So let me first plot the stress diagram. This we have assumed 150. This you have got C, and here you have T. Okay, so this is X bar and this is D. That is total D minus cover. Okay, so moment will be C into X bar plus P into, which is also equal to P. So T into D minus. Yes. P कहाँ होता है? B तो लगाया नहीं है। तो कॉलम में P equal to 0, then it is B. But it's good that you remember that if it is column, we have to be careful. Then we can't take moment about any axis. We have to take it about sinusoidal axis only. But if it is beam, then you take about any axis, answer will be same. So anybody calculated 5i? Nine point 06 units. What are the units of curvature? In 10 to power minus 5 per meter. Per mm decide कर लो फिर per mm. What should be the unit of curvature? What is curvature? Rate of change of slope. What are the units of slope? Radian. Radian is unitless. Okay. And curvature is slope per unit length. So whatever units of length you are taking, same will be length of it. Strain is unitless. If you are taking the D in millimeter, then you will get this per millimeter. If you are taking D in meter, then you will take per meter. So it is strain, that is 0.0015 in our case, divided by 150. That will be it. 0.009 and 10 to the power 6. 10 to the power minus 6 are. So it is simply 0.0015 divided by 150.
Sir, we have to use effective depth for calculating 5.
Either way you can do it, answer should come out to be the same. So strain diagram is like this. I have calculated this. So this is this strain which we have taken 0.005 divided by this height. अरे भाई ये strain भी तो उसी के according आएगा. This will change. So you can calculate this, or total. I told you, 3 expressions you have given for 5. All the 3 expressions will give you same answer. So it is 1 into 10 to the power. For 150, what I have to do to make it 150? How much I have to multiply? 4 10 to the power 5 minus 50. So 1 into per millimeter. How much will be per meter? 1000 डिवाइड करेंगे मल्टीप्लाई करेंगे?
Multiply.
So that is equal to 1 into 10 to the power minus 2 per meter. So can you calculate EI effective? How much? 19200 unit kilonewton.
Meters.
Let us calculate how much is EI. We also call it EI gross. That is equal to EC into BDQ by 12. So how much is that? In case of steel, we have seen EI effective was equal to EI gross. Let's see how much we get here. So EC 5000 under root FCK. So we are using in gross, we are using एक हाँ
Sir, this FCK will be expected strength, na? FCK plus 1.64.
you can do that also. It's up to you. Okay. But let us calculate it. When we say EC, not ECE, EC, okay, we can take it 5000 under root FCK. And B 300 into 400 Q divided by
We have compared the EI effective structural and EI structural. So we have to multiply the structural also. That is FCK is
So you can do for that also. It won't make much difference. I'm just saying that let us take EC of what you are doing in your normal calculation. Yes. Expected strain वही होगा. हम ECIG से ले रहे हैं, not ECEIG. We can compare with anything. Let's compare with ECIG. The EC which we are normally. यहाँ E का वैल्यू हमने निकाला ही नहीं. We have taken total EI factor. Suppose you were modeling this column, how you would have calculated its stiffness? E, whatever you are taking expected or characteristic, whatever you are taking into BD cube by 12. So let us compare with that stiffness which you would have been calculating. Okay, and conventionally it is taken as EC. We are comparing with EC. That doesn't mean that the concrete has EC or ECE. Just we are comparing with EC. EC into I. So how much this comes out to be?
43818.
43818. Okay. So how much is EI effective divided by ECIG? Point? So you can see that effective EI is only 44%. And this we have calculated by any randomly assumed reinforcement. Okay. If you will consider the realistic reinforcement which usually we get, okay, it comes out to be roughly 30%. 0.30 to 0.35, 30 to 35%. But what I want to understand you here is that the effective stiffness of RCC section is much less than the block. Yes.
As per the code from 70% and 30%, not
We will come to that. That is for power, not for B. How much is for B? 30. We will talk about that. But it is low. What you have to understand is, in case of steel, it was ES BDQ by pi. Here it is much less than EC BDQ by pi. This you have to. Okay. So now you can calculate mu and phi u also. What will be the condition at mu? What is strain at mu? Steel has reached the ultimate. Means steel has reached, we are using Fe500, so steel has reached 14.5% or 0.145. Okay, you can do that. And what will happen there at to concrete? If concrete is not yet crushed, fine, you can use that. But usually you will see the concrete will get crushed much before. So there also the concrete is going to come out. Okay. So how you will obtain? When the concrete reaches, in this case, how much maximum strain concrete can take? 0.0035. If it was confined, then the concrete would have taken more strain, epsilon CCU. But now the strain of concrete can take epsilon U equal to 0.0035. So please do that case. That is simpler than what we have already done. So please complete that case. Calculate mu and phi u also. And when we meet day after tomorrow. At 4. Yeah, Wednesday we will meet at 4. So when we meet at 4 on Wednesday, we will continue from here. Please complete that. So then we will move to the member now, a cantilever. How we can calculate from moment curvature curve, load displacement. Sorry?
in this case we don't consider the P value.
Yes, P is 0. You can do it with the value of P also. Flows